Another consequence of relativistic special relativity, as I mentioned, we have the Lorentz transformation. That gives us transformation x, y, z, t from one reference frame to another reference frame. And both reference frames are moving with respect to each other with a constant velocity. And as a consequence, we had the time dilation, the length contraction, simultaneity of event. But now we have also, since the position and the time are affected, the velocities are affected, and the quantities that depend on the time and distance or position will be affected. One of them is the momentum, so the relativistic momentum. So the relativistic momentum becomes momentum is equal to gamma, the mass of the particle at rest, and the velocity of the particle. Okay, with gamma is 1 over 1 minus v over c squared, and this is the speed of the particle or the object. Okay, another consequence is the kinetic energy. Kinetic energy is mc squared gamma minus 1. So this is the kinetic energy. Relativistic momentum, kinetic energy, to be consistent, kinetic energy, and total energy. Okay, so the total energy will be equal to the kinetic energy plus mc squared, and for that we define a quantity that is equal to mc squared, and that is called energy at rest. The energy at rest. Okay, and then there is another formula which is very interesting, is the relationship between the total energy and the momentum and the energy at rest. The total energy squared is equal to momentum squared c squared plus m squared c4, or it equal to p squared c squared plus E0 squared, which is the energy at rest. Now, interestingly, most of the energy, whether kinetic energy or total energy, is expressed in electron volt, in mega electron volt, kilo electron volt, giga electron volt, etc. So electron volt. So okay, so 1 electron volt is equal to 1.6 10 to the minus 19 joule. So the energies that we are dealing with are always expressed in EV, keV, MeV, GeV, or tera electron volt, or whatever. Okay. So now the momentum, so the kinetic energy will be expressed in electron volt. Let's say mega electron volt. 1 mega electron volt is 10 to the power 6 electron volt, okay, for example. Total energy will be also expressed in MeV or EV in general. Okay, the rest energy, will be expressed in MeV or keV, and the momentum will be expressed in MeV per c. C is the speed of light. And because we have the famous equations, the total energy is also equal to gamma mc squared. So the total energy is also equal to gamma mc squared. This one, I forgot to mention it above. So it's equal to gamma mc squared. Okay. And the rest mass is also mc squared, the rest energy, So this is given in MeV. And because there is an equivalency between the mass and energy, now the mass can be also expressed. So the unit of the mass now becomes MeV per c squared. Okay, like if the mc squared is given an MeV. So this means the unit of the mass can be given an MeV, and this c squared is brought here. Okay, so just to summarize, we have those 5 equations. This is equation number 1 for the momentum, equation number 2 for the kinetic energy, equation number 3 for the total energy, equation number 4 for the total energy, and equation number 5 for the total energy, in addition to the fact that the energy at rest is mc squared. Now, let's compute an example. Let's compute the energy at rest for the electron. So we know that the mass of the electron, so the energy is equal mc squared, right? We know that the mass of the electron approximately is 9.1 10 to the minus 31 kilogram. Okay, so this gives me, well, 9.1 10 to the 31 kilogram times the speed of light. Speed of light is 9 squared. It's 9 10 to the power of 16. Of course, since this one is in kilogram and this one is in meters squared per second squared, so the result will be in joule. Okay, the result will be in joule. Now, if I want to convert this to mega electron volt or 2 electron volt, then what I have to do is to divide this quantity by 1.6 10 to the minus 19. This will give me the result in EV. And then if I want to convert it to mega electron volt, then this quantity, I will divide it by 1 million. This will give me the result. And if you do the calculation, you will see that the energy at rest of the electron is 0.511 MeV. Okay, this is a very, very famous or a very famous quantity, or 511 keV. Okay, we can also try to calculate the energy at rest for the proton, or the energy at rest of the proton. You will see that the energy at rest is 938 MeV. Now, let's go back to the electron. So the energy at rest of the electron is 0.511 MeV, right? Which is also equal to mc, the mass of the electron, c squared. So now what we can do is the mass of the electron then becomes equal to 0.511 MeV, but this c squared, we brought it part of the unit. So the mass of the electron will be 0.511, the same value as the energy at rest, but the unit is different. Okay, so that's something that we need to be careful about when we deal with the unit in relativistic energies and momentum. Okay, so I will stop here, and the next video I will do some examples.